In this example, we're asked to use a theorem to show that this given set is a vector space. I want to do that using theorem 4.2.1, which says that the null space of an n by n matrix is a subspace of Rn. So remember that the null space of an n by n matrix would be the solution set to this equation. So it's the set of vectors x for which a times x is equal to the 0 vector. That's the null space of the matrix A. So the trick in this problem then would be to write this set W as the null space of some n by n matrix. So let's see what we're given. So W is a set of three-dimensional vectors that satisfy these two equations. Now the two equations could be rewritten by moving over the R terms. So P minus 3Q, and then move the 4R over, so minus 4R is equal to 0. And 2P minus 3Q minus R is equal to 0. Now that system of equations could be expressed as a matrix equation, where we put the coefficient matrix here, so 1, negative 3, negative 4, and then 2, negative 3, negative 1. So here's our coefficient matrix times the vector PQR is equal to the two-dimensional 0 vector here. And just to verify this real quick, so if we do this matrix multiplication, we'd have P minus 3Q minus 4R is equal to 0, the first equation. And then 2P minus 3Q minus R is equal to 0, so there's the second equation. So we're confident that this matrix equation corresponds to this set of linear equations. And so now if we call this matrix A, and we call this vector x, then we have expressed W as the solution set, the set of vectors x for which a times x is 0. But this is oh, sorry, I keep doing things I don't mean to do, the null space of the matrix A. This is where A is, let's see, 2 rows by 3 columns, so it's a 2 by 3 matrix. So this is a subspace of R3. I'm sorry about my writing here. But that then does prove that this set of three-dimensional vectors is a vector space.